On September 14, 2015, at approximately 9 hours 50 minutes and 45 seconds a.m. Pacific Daylight Time, the Earth was shaken by a gravitational wave. It may sound like the beginning of a science fiction movie, but this is actually a scientific fact. In 2015, the Laser Interferometer Gravitational-Wave Observatory, or LIGO, detected the first ever gravitational waves. This detection confirmed a major prediction of Einstein's theory of general relativity, which was developed more than 100 years ago, and it opened up an entirely new way for us to listen to the universe. Join me today as we look back at the incredible story of gravitational waves. What are they? Why were they so important when they were discovered? And how have they changed our view of the cosmos? This is the story of gravitational waves. I'm your host, and you're watching this channel. It was in 1916 that Albert Einstein published his theory of general relativity. He showed that gravity wasn't a force as such, but rather a manifestation of the curvature of spacetime. Imagine spacetime as a sort of trampoline. If you place a bowling ball on the trampoline, it will make an indentation. If another bowling ball is then placed nearby, it will roll towards the first one. Spacetime is much the same. If you place a heavy object into spacetime, it will cause an indentation. Other objects will then move towards it under the influence of this curvature. This is how gravity works. Einstein also predicted that if two massive objects were to collide, they would shake space-time around them, creating ripples in the fabric of reality that travel outwards at the speed of light. These are known as gravitational waves. Although he predicted their existence, scientists wouldn't come up with a way of detecting them for another century. The idea of gravitational waves can be hard to wrap your head around. Just think about the size of our universe. How big do you think a gravitational wave is? Well, as it turns out, it's not very big at all. A passing gravitational wave only stretches and shrinks space by a minuscule amount, typically less than 1 part in 10 to the 21st power. That's a 1 followed by 21 zeros. To put this in perspective, if our solar system were affected by a passing gravitational wave of this size, the distance between the Sun and Pluto would only change by 1 atom's width. It's this tiny distortion in spacetime that makes detecting gravitational waves so difficult. But it's also what makes them so useful as a tool for astronomers. You see, visible light only has a limited range of wavelengths. There's shorter wavelengths like ultraviolet and X-rays, and longer wavelengths like radio waves and infrareds. However, gravitational waves can stretch and shrink space across a huge range of distances. This means that they can carry information about events that are much larger and more energetic than anything we could observe using light alone. But there was still a problem. Even though Einstein had predicted the existence of gravitational waves 100 years earlier, no one had been able to detect them. And so in 1990, a group of scientists from various universities and institutions got together to try and solve the issue. They would go on to form the Laser Interferometer Gravitational-Wave Observatory, or LIGO. The plan was simple. Build two observatories thousands of miles apart that could measure the incredibly small distortions in spacetime caused by gravitational waves. To do this, they would construct the world's largest and most precise interferometers. An interferometer is basically a device that uses lasers to split and recombine beams of light in order to precisely measure distances. The first LIGO detector was built in Hanford, Washington. It consisted of 2 perpendicular arms, each 3 kilometers long. The second detector was built in Livingston, Louisiana, and had the same dimensions. Both observatories were completed in 2002 and began operations in February of 2003. Here's how they work. A laser is split into 2 separate beams. Each beam travels down one of the arms before being reflected back towards the starting point. Once the beams recombine, they're supposed to cancel each other out. However, if a gravitational wave passes through the interferometer, one arm will be slightly stretched while the other is slightly shrunk. This means that when the beams recombine, they won't cancel each other out. A photodetector can then pick up this tiny change, indicating that a gravitational wave has passed through. While the interferometers were turned on, scientists analyzed data looking for any sign of a gravitational wave. But despite coming up empty, they continued to collect data every day for nearly 10 years. Then, in September 2015, it happened. Scientists detected a gravitational wave that had been created by two black holes merging together. The signal was faint, but it matched the exact frequency that physicists had predicted. When this discovery was announced to the public, it made headlines around the world. Scientists who had worked on the project for decades were jubilant. They finally had proof that Einstein's theory of general relativity was correct. For their groundbreaking work, the scientists behind LIGO shared the 2017 Nobel Physics Prize, but the story doesn't end there. You see, now that scientists knew that gravitational wave detectors worked, they could start searching in earnest. Since 2015, LIGO has made dozens of discoveries. For example, in 2017, they detected a collision between two neutron stars. This event also generated a tremendous amount of energy, allowing scientists to detect the first ever gravitational wave background. This is a faint hum that's generated by all the gravitational waves that are passing through space at any given moment. LIGO has also made some remarkable discoveries closer to home. Perhaps even more exciting is the recent announcement that LIGO has made in tandem with the European Space Agency's ELISA mission. Together, they detected the gravitational waves produced by merging black holes. 3 of the black holes formed a sort of three-way tie, and the fourth collided with them after being ejected from the trio. It's one of the most dramatic collisions ever witnessed, and it gave scientists unprecedented insight into the behavior of extreme gravity. Now, if you want to learn more about the incredible science that goes on at CERN, I've recently launched a course on Brilliant. That'll take you behind the scenes of the world's largest particle physics laboratory. Ulines learn what really happens inside the Large Hadron Collider and what it means for our understanding of the universe. Ulines also get to explore some of the other amazing experiments that are taking place at CERN right now, such as the search for dark matter and antimatter. Each lesson builds on the last, so Ulines finish the course knowing everything there is to know about this incredible place. And that's just one course among many others. With over 60 courses available, there's something for everyone on Brilliant. Whether you want to learn more about gravitational waves or any of the other incredible discoveries that are being made at CERN, you'll find a course that interests you. So, if you're ready to learn more about the incredible science that's being done at CERN, that was the story of gravitational waves. All the best, and see you next time!